will describe a permanent wireless monitoring system installed in new Carquinez Bridge in Vallejo, California. Ready, are you presenting? We're ready to go. Okay, so President Jeremy, professor from the University of Michigan, and we have some ready to go. Okay.
So the movie is going to be narrated by my postdoc and student, Dr. Kurata, and Ivan from this company.
New Carquinez suspension bridge locates in Vallejo, California, forming a direct route between San Francisco and Sacramento. The bridge was constructed in 2003 at a total cost of $240 million to replace the original Carquinez Bridge, which was constructed in 1927. The main structural component of New Carquinez are two concrete towers, a steel orthotropic box girder, two anchorages, and suspension cables. The main span of the bridge is 728 meters, while the total bridge length is 1,056 meters. As a relatively new bridge in operation less than 10 years, there are no major structural deficiencies yet reported for the bridge. Our research team is proposing a wireless monitoring system specifically designed for long-span bridges, utilizing low-power wireless sensor networks and IT technology for effective data management. This is the schematics of cyber-enabled wireless monitoring system. The lower tier consists of sub-networks of low-power wireless nodes. Wirelessly collected data in the networks are transferred into remote server on the upper tier via internet. On the upper tier, the cyber environment centrally manages data and supports secure and flexible access to stored data from system end users. The Narada wireless node, previously developed at the University of Michigan, is adapted and modified for long-term deployment in harsh field settings. The wireless sensor network must achieve a number of operational requirements to be suitable for long-term monitoring of large-span bridges. The left photo shows a Narada node with a power amplified radio, which can achieve line-of-sight communication range of 700 meters. A Narada node interface with transducers such as triaxial accelerometer is prepackaged and pre-tested prior to shipping. Here is a view of prepackaged nodes attached underneath the bridge girder for monitoring bridge dynamic responses. These nodes are able to continuously operate for a long period, harvesting power from solar panels deployed on main deck. Climate sensors such as anemometer, thermometer, and humidity sensors are also deployed on the main deck. Narada servers operate either on solar panel or electrical outlets equipped at the bridge tower locations. The server runs on Linux system installed on industrial-grade single-board computers. Currently, the 3 Narada servers deployed on the bridge collect data from 28 Narada nodes with 81 sensing channels. Transmission and storage of collected bridge data are centrally managed by cyber environment frame networks named SenseStore. Secure but convenient access of data are provided for data providers and consumers through the communication of client-server application interfaces. In current configuration, data collection is initiated by on-site Narada server at scheduled time. Data collected at bridge sites are sent to remote server using 3G phone networks. We are going to get remote access to one of the servers through SSH tunnel. First, redirect to Narada program folder and run Narada program. On the welcome page, we selected an option to check current status of the entire network. Now you can see on the server, there are 11 units standby for sensing. In autonomous sensing, Narada data acquisition is triggered every 4 hours by the operating system through the cron tab program. But for the demo today, we manually run the Narada program. Normally, for each sensing cycle, we collect data for 8 minutes, but for demonstrations, we only collect data for 20 seconds. Unit ID and channel settings for each unit are also registered in this file. Now we are ready to run Narada program. Narada server triggers all the Narada nodes for sensing, and the summary of data acquisition setting shows up. When data acquisition completes, the Narada nodes wirelessly transmit data to the Narada server. Through 3G phone network, the Narada server opens a proxy for each sensor channel and transfers data in a secured manner. In the end of scheduled sensing cycle, we put Narada nodes into sleep mode for power saving. Our cyber environment is able to handle multiple Narada servers at the same time. Currently, the Narada servers are set to trigger sensing for 8 minutes every 4 hours. Sensor server consisted of hierarchical database called HDF5 and relational database called SQL. Sensor readings are stored in HDF5, while rich geometrical details and sensor configurations are stored in SQL relational database. The ontology and structure of database are centrally managed by database code generation tool. Using the sensor web viewer, the schema of sensor and stored data can be viewed from anywhere in the world. For example, in the class of DAQ unit, 29 Narada nodes are registered. For each unit, up to 4 channel objects are created in the class of DAQ unit channels. The sensor server creates channel data objects whenever the Narada servers upload the data from the bridge site. Data on single channel is easily accessible by clicking the calendar. By selecting the date on the calendar, one-day data on single channel can be downloaded in Excel format. The downloaded data file includes timestamp and raw sensor readings. In the sensor table, a unique ID is assigned to each sensor type. This table shows the summary of sensor channel created for each sensor type. Connection between sensor channel and Narada node ID is shown here. Table also contains timestamp of channel creations. The location and orientation of sensors can be stored as well. Media files are also stored in HDF5 database. Currently, north and south servers underneath the bridge girder send photos of new Carquinez every 4 hours. Let's open a north tower photo taken on August 29, 4 p.m. These webcam photos with data interrogation services, where client application interfaces are implemented to access stored data in the sensor server.
Now we're going to call a Python script, which is designed for autonomous logging for the status of Narada nodes and the reliability of wireless communication. In this demo, we'll make...
Due to the interest of time, I will just summarize very briefly. Our interrogation services are able to tell if there's faulty sensors on the bridge. We also have automated modal analysis methods and statistical methods that actually can autonomously screen the data for information that's pertinent to the end user of the system, which in this case would be Caltrans. So this is actually a log of the faulty sensors, and then one of the algorithms we have implemented is the frequency domain composition method for the generation of mode shapes on the bridge using the data that's been stored inside the StemStore database. So with that said, if there's any questions, we'd be happy to answer them at this point in time.
Any comments or questions? Well, thank you.